Okay, I should stop and leave a little time for questions. I hope I've showed you that with these drop-based microfluidics, we certainly can make new materials. We can make new materials in sufficient form that you can go out and buy them. And we have really what's probably the most important thing. We can shrink the City University of Hong Kong to a chip. And so with that, let me stop and take questions.
Now is open for questions. Any questions?
No, if you don't ask me questions, I have questions for you.
Yeah, you want to ask a question?
Very good talk. From a fundamental point of view, what's the smaller size, for droplet to good?
What's the which?
What's the smaller size?
Okay, what's the smallest size that you can make a drop? Yeah. So I'll give you a practical answer, and then I'll give you a fundamental answer. So I'll give you three answers. The fundamental answer is that all the physics that goes into making drops will work down to length scales until surface effects dominate. And that's down to length scales of a few nanometers. There's two problems with that. The first problem is that one of the fluids almost always is water or something aqueous, and water always has dust in it. It's really hard to get rid of dust. Dust is 5 microns in the diameter, and anytime you have orifices smaller than 5 microns, they clog because of dust. And we're lazy as hell, so we never work at sizes smaller than about 5 microns, just for that practical reason. What's the fundamental reason? It's probably not the surface, but rather it's you're making one of the other fluid is probably an oil. And oils have this unusual property, most oils have this unusual property, that their viscosities diverge with hydrostatic pressure. So as you make it smaller and smaller to make the things flow through smaller and smaller channels, you need higher and higher hydrostatic pressures. As you increase the hydrostatic pressure, you actually increase the viscosity of the oil. Eventually you make it so viscous that it doesn't flow. So that's probably the practical, fundamental answer if you filter things and get rid of the dust.
Any other question? Yes?
Yeah. You have used method into product some makeup production, and I want to ask you, what's the advantage of this method to human health compared to other conventional methods?
Okay, so human health, think drug delivery. Cosmetics are not really meant for human health. Do you know why you use cosmetics? Anybody know why I use cosmetics? Anybody know? It's really simple.
That's amazing.
Better.
You feel better. Exactly right. You want to feel better. That's exactly right. That's what you use. So what's really cool about this, that product by Chanel, what's really cool, remember, you're making each drop separately. So you can make each drop separately, and you can use a reaction. It's basically a charge reaction that's called coacervation. You make a very thin shell while it's flowing down before it interacts with other drops. And so you can make an emulsion that has no surfactant. And surfactants are not good for emulsions because they make it sticky. It doesn't really feel good. So now you can make a cream that has no surfactant. And you put that on your skin, and it feels totally differently. It's basically glycerin, which moisturizes, in water, mainly water. You put it on your skin. It feels like you're just rubbing water on your skin. You rub it, and all of a sudden, it bursts because you've dried the water out. It bursts, and you feel this burst, and then the moisturizer goes on your skin. Completely different skin feel, so it feels completely differently, but it's made, you can't make it in any other way because you can't use surfactant. So you can make things, again, that have a completely different sense, that feel completely differently, and that's the appeal of that particular product.
Yes. Oh, maybe Stella first, then you second.
When you try to use the droplet to encapsulate different cells or particles, how are there limits on how precise and how many different types of mixture of species that you can include in a specific droplet?
So okay, so now you're asking maybe a slightly different question. Could I put more than one cell and a different type? The answer is, with some, depending on the degree of control and the degree of sophistication I want to do, the answer is sort of arbitrary. If I want to mix, say, several cells, if I don't care that I have exactly one of each, then I can just increase the concentration, and I can just mix two streams, and I can very easily mix pairs of cells. And we do that a lot. If I really insist on having a pair of cells, I could do a trick. Like I could put one cell into a little bit of a gel. So I make it a round particle. I could select those pieces of gel that have the cell, and then I can inject one cell per drop, and I can pico-inject. I can inject the second cell in. So I can do things like that. And if I want 3, I can just do that several times. So depending on the sophistication that you want, you can do a lot of things. If you want to make things pretty quickly and pretty easily, you use just random statistics, and then you get some random. But again, you can create drops so rapidly and so many that it's often not so bad just to do it randomly.
Thanks for the very inspiring talk. I'm also interested in the cell encapsulation. So when you are doing cell encapsulation, do you have some consideration about the material, because it will affect the permeability of the exchange of material between the cell and outside?
A lot of consideration.
Yeah.
So
What will be your advice?
well, it depends what you want to do. If you want a cell to survive for, we figure about 12 hours, we just put the cell in a drop, and in our normal devices, it turns out that gases are totally permeable through the oil and through the material that we make the devices. And so the gas can exchange very easily. What the cell can't do is exchange its nutrients. And so if we want to do that, what we do is we gel the drop, and then we wash away the oil, and we have the cell encapsulated in a gel. We can diffuse in medium or whatever we want. Those can live indefinitely. They can propagate, they can divide. And then if we want to do more work on them and really look at individual behavior, we'll emulsify that oil back into we'll emulsify those gel drops back into oil and go back and do the same experiments that we did originally.
Mm-hmm. Thank you.
Thank you for your lecture. I have a question about how you control the microfluids in your system. For example, in circuits, we use gate voltage for on or off to control the electron flow, and in pipelines, we use waves to control the water, oil, or something else. So how about in your system, a microfluid system, how do you control the flow of the microfluid? So is there any waves or similar thing? Thank you.
You can do a lot of things like that. There is a whole technology which I don't describe where people use valves to control the fluid. We don't. It's too complicated. We can use electric field. So I showed you how you can steer drops. So we can make circuits where we use electric fields, and we can steer drops and switch them in and out. We can do things like that. We can make drops that circulate and pull them out. We can make drops that go back and forth. We can put drops in arrays and look at them, operate them, and then bring them back out in an ordered fashion. So we have some control, not complete control. So sorry, you really can't shrink the university down. You still need your laboratories.
Thank you.
Another question? Yes, at the back.
Thank you for your talk. It's very inspiring. I have a fundamental question, and this maybe I missed it. How does it? Because in this video, in this animated sequence, the drop it forms a droplet, but it doesn't attach to the other droplet. So I'm very curious how do you prevent two droplets from binding together again?
So anybody who's worked with emulsions knows that the scourge, the problem with working with emulsions, is to prevent the coalescence that you're talking about. But it turns out the solution is fairly simple. You use a surfactant. So what I don't tell you here is there's a surfactant in the solution, and that coats the outside of the emulsion and prevents them from coalescing.
Another question? Since I'm a chemist, right? Okay, so I'm trying to use my imagination. So most of your droplets are based on the water phase, right? So have you ever tried anything related to organic based system?
The key is to make drops, you want to use typically immiscible fluids. And so you need any pair of immiscible fluids. So we can use silicon oil and mineral oil, silicon oil and fluorinated oil, or aqueous solutions, or DMSO. So we can use a variety of different things as long as they're immiscible or relatively immiscible. I will say that the one exception to what I said is Anderson, who works at Hong Kong University, has worked very hard on making drops with miscible fluids. It's a whole new subject. But what we do is work with immiscible fluids. And so yes, you can use organic fluids as long as you can find a second immiscible fluid.
Yeah, besides some of the the preliminary, those are oxidation reaction you show, right? We reacted with hydrogen peroxide. And have you ever tried any more sophisticated chemical reactions? Okay, within those small reactors, okay, droplet reactors.
Okay, so what you're asking, have we done chemistry
Yeah.
in the drops? And we haven't done a whole lot of that, but there's no reason you couldn't. We're not chemists, so we don't know what to do. So if you would tell us some good suggestions, we'll try it.
Okay, so maybe we can talk about during the dinner time.
Excellent.
Okay, any other questions? Yeah, if no further question, please join me to thank Professor Weitz for the wonderful talk. Yeah. This souvenir.
Oh, thank you so much.
Sure. Okay, thank you.
Thank you.
Yeah, thank you very much.
Thank you.